This view is a detailed view, really, as much as necessary. There are lots of other things like shafts and couplings that are not necessary, but the heart of the device is there. And as you can see, you were not able to see this at the booth or last night at the aquarium, the internal details of the device. This member here is what we call the rotor, but of course in this case they're both primary and secondary member are both rotating. So this, for the sake of argument, let's call this is the rotor, and this the can. That's the term that we used in the paper. The rotor is very similar to what you would see normally in an induction motor, a squirrel cage, what we call a squirrel cage induction motor. The reason why they call it a squirrel cage is because of the multiple bars that lie within those slots. And these bars are shorted by a ring on this side and another ring on the other side. So without these steel plates, you can imagine the rest is like a cage, hence a squirrel cage, unfortunate squirrel. So the technology involved in the construction of this member, the rotor, is no different than any other induction motor that you can buy commercially. The other member, the can, as you can see here, is populated by a bunch of magnets. These magnets are radially oriented and they alternate between north and south. So if you are familiar with brushless DC motors, you would recognize this member as being very similar to a brushless DC motor. No wires, no winding, no nothing. These magnets are energized and assembled in the can, and that's the end of it. Now, what happened here is combining induction motor technology with brushless DC motor technology using permanent magnets as the brilliant breakthrough that Mr. Corbin came up with. And putting them together resulted in a type of behavior that frankly hasn't been seen in motors, that stick with motors for now. What's happening is that the permanent magnets are inducing currents in the cage of the secondary member and thus maintaining magnetic contact between the two without physical contact. Torque is therefore transferred from one member to the other. It doesn't matter which direction it is. The device doesn't know the difference. Hence, you have a device that has no electrical connections, does not rely on eddy currents, and does not consume power in the sense you don't have to feed it with any electrical power, but is capable of transferring torque, and therefore power, from one member to the other. Now this fits very nicely with the definition of a coupling, and that is one of the possible uses of this device. You see here on the left, you'll work that out. On the left, the device, the very same device we just talked about, where the outside can is fully covering the inside rotor. Hence you see this solid mass, you don't see the rotor anymore. This is fully engaged position of the device, and therefore it is the position where you can transfer the maximum amount of torque from one member, the primary, to the secondary. Now, if you take the same device and axially separate or disengage one member from the other, the primary from the secondary, the phenomenon that happens is very interesting, and that is you start transferring the torque from one part to the other, but at different speeds. Speed actually starts to change depending, not linearly, depending upon the amount of engagement between the primary and the secondary. And it turned out that because this is following induction motor theory, as you will see, it follows more or less induction motor principles and torque curves. And that is an advantage because we know so much about induction motors that we can manipulate the design of this device to produce virtually any characteristics we want, just following that knowledge from induction motors. But the fact remains that the very same device can be used fully engaged as a coupling, if that's what you need, but can be an adjustable speed drive, again, if that is what you need. without any change to the design. Now, as an outcome of the experimentation and knowledge we gained from prototyping, we discovered, or the company discovered, that as a coupling, this device just provides virtually free feature that has been a problem for induction motor designers and like me and users, which is every time you switch an induction motor on to drive a pump or whatever the application is, you are guaranteed to draw a huge amount of inrush current. That is the nature of the beast. Induction motors are virtually a dead short circuit on the supply when you turn the power on. And of course, they get better as speed picks up and current drops. So that inrush current, you have to anticipate, you have to know about, and therefore provide the means for coping with that in terms of your supply, in terms of your relationships with your neighbors, if they lose power. So what we discovered is when you use these couplings, that the gradual ramp up of speed of this coupling automatically solves the problem in that it allows your load to pick up speed and end up at the final speed without taxing your motor to the extreme limit. We'll look at that in a minute, and I'll show you the curves that demonstrate this behavior. But starting off with the normal characteristics that we get from one of those devices, and by no means this is the only shape. For you people who are familiar with the induction motor characteristics, you would recognize this as what you get from a textbook, from a catalog. It's a plot, where's the mouse? A plot of the torque coming out of the motor, or the coupling in this case, versus the speed. And you notice when the speed, the output speed, this is the slip speed. So, well, we can start from this end. At start, the output speed is very low, and therefore the amount of torque being produced by this device is high. It travels along this line as the speed at the load is increasing, and then it reaches a peak, and depending upon where you're going to end up with, at what speed, you will end up at the amount of torque that's prescribed by that curve. This happens to be the curve for full engagement. If you decide to reduce the engagement between the can and the rotor to a different amount, less than 100%, you notice that you start traveling on different curves that are similar in shape but lower in value. So you have really an infinite choice of operating points here in all this area of whatever speed you want to operate at, depending upon the torque you want to get to the load. And of course, you do that by choosing the engagement between the two members, either by hand, as you saw last night at the aquarium, or if you want to attach an actuator, a closed loop, whatever, that's dead easy. So these are refinements and improvements on the type of control.